All right, so in this section, we're going to be beginning the probability. So we're going to begin talking about probability and counting. So I want to go ahead and start by defining what a probability experiment is. Okay, so a probability experiment is simply an action or trial through which we're obtaining specific results. Now, there's a few parts of this, so these are some vocab words that we will use over and over again. So the results of a single trial in the probability experiment is called the outcome. The set of all possible outcomes is called a sample space, and this should be event. And an event is a subset and an event is a subset of a sample space. Okay, so taking a look at number 1, it says for each probability experiment, determine the number of outcomes and identify the sample space. Part 1, a probability experiment consists of recording a response to the survey statement to the right and the gender of the response. Okay, so we have three possibilities through this survey, and then we have 2 possibilities whenever we're dealing with gender. So gender, we have male or female. Okay, so I'm going to set this up using a tree diagram. Okay, so let's go ahead and start our first row with the possible responses that we have. So we have yes, we have no, we have not sure. Okay, and it's okay to abbreviate these as long as you know what you're talking about. All right, so then let's say we chose, they said yes. Well, that person could have been male or they could have been female. Same with no, they could have been male or female. And not sure, they could have been male or female. Okay, so when we're looking for the number of outcomes, what we're looking at is we're counting this bottom row. Okay, so we're counting the number of outcomes in this bottom row. So when I answer this, we get 6. So we have 6 possible outcomes. Okay, now the sample set, or the sample space, is a little different. This is a set, so we're listing all of the possibilities. Okay, now when I look at this, I'm going to say, well, on the first row, they could have said yes, and they could have been, so they said yes, and so yes people could have been either male, or if they said yes, they could have been female. Okay, then if I were to look at no, so what if they entered no? Well, the no people could have said they could have been male, or again, they could have been female. Okay, then if they said not sure, once again, they could have been male, or they could have been female. So not sure, could have been female. Okay, but those are the all 6 possible outcomes. So notice that these should line up with the number of outcomes. We've got 1, 2, 3, 4, 5, and 6. Okay, so let's take a look at this next one. All right, so it says the probability experiment consists of recording a response to the statement in 1, and the age ranges from 18 to 34, 35 to 49, and 50 and older of the respondents. Okay, so just like we did just on the top one, we're going to go ahead and break this up into a tree diagram. Okay, so we're going to set this up as a tree diagram. So we've got yes, no, not sure, and then we're going to break this up into, well, we've got 3 categories, 1, 2, and 3. Okay, so I'm going to go ahead and just to save on some time, I'm going to label this one as, not this one, I'm going to label this one over here as 1, this one as 2, and this one as 3, just to save on some time. So if we said yes, well, we could have been an age range 1, 2, or 3. No, they could have done 1, 2, or 3, and then not sure, they could have said 1, 2, or 3, or they could have been in those age ranges. Okay, now if we were to look at the number of outcomes, okay, so outcomes here, well, we have on the bottom row, we have 3, 3, and 3, so we have a total of 9 possible outcomes. Okay, and we'll do the same thing with the sample set. Okay, so sample set is simply the set. Well, they could have said yes, and age range 1. They could have said yes and age range 2, yes and age range 3. They could have said no and 1, no and 2, no and 3. And then finally, they could have said not sure and 1, not sure and 2, and then not sure and 3. Okay, so notice that again, we do have these 9 outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and so we can do the same thing down here. Okay, I'm going to go ahead and skip number 3, but I'll leave that to you if you choose to give yourself another example. Okay, but do know that the total number of outcomes here, you should end up with 12. Okay, so when you're doing your sample set or your sample space, you should have a set of 12 numbers. All right, so now let's go ahead and talk about a simple event. So a simple event is it's an outcome. It's a single outcome. Okay, so it's an event that consists of only one possible outcome. All right, I'm going to go ahead and give you guys this quick example. It says you have a coin and a die. The event that you flip a heads and roll a 6. Okay, so we're looking at the event that we flip a heads and roll a 6. So notice that if we were to build a tree diagram, okay, so let's say we built a tree diagram. So heads, tails, and then heads we have 1, 2, 3, 4, 5, 6. Tails we have 1, 2, 3, 4, 5, and 6. Okay, so notice that if I were to look for just a heads and a tail, a heads and a 6, so I'm going to follow this path. So I follow it over here. I've got a heads, and then I've got a 6. There's only one possible way that we can get this outcome. So we have exactly one outcome. Okay, so this would be a simple event. Okay, if we were to look over here and say, well, what's the probability of flipping a heads and rolling an even? Okay, in this case, notice that if we flip a heads, so if we flip a heads, we have 6 possibilities, right? So we have 6 possible outcomes over here. And on the other side, though, notice that if we flip a tails, well, the only even numbers here are 2, 4, and 6. So in this case, we have 3 possibilities. So we have a total of 9 outcomes. Okay, so this one would be not simple. Okay, so simple is if you only have one path that you can follow. Not simple is if you have multiple paths that we can follow. All right, so let's look at this next example. It says, determine the number of outcomes in each event, then decide whether each event is simple or not, and then explain. So it says that for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So we're looking for exactly one machine part that's defective. Okay, and so in this case, we actually only have one outcome that we're looking for. We're just looking for that defective machine part. So this is just determined. This is a simple event. Okay, and again, it's because we're looking for that specific. So that word specific tells us that we're looking for that one defective part. Okay, now let's look down here. We have a 6-sided die, and we're looking at rolling at least a 4. So the possible outcomes here, if we were to rolling at least a 4, well, we could have 4, we could have a 5, or we could have a 6. So how many outcomes are there? So there are 3 outcomes. Okay, and because we have 3 outcomes, it is not simple. Okay, so again, the difference being is that we're looking for a specific defective part on the first one. And down here, we have 3 possible outcomes that we're looking for. All right, so the fundamental counting principle, it says that if one event can occur m number of ways and a second event can occur n number of ways, then the number of ways the 2 events can occur is the sequence n times m. And we could extend this. So let's say we had an O or a P or a Z. All we would have to do is take the number of ways that they can happen and simply multiply them up. So, for example, here we have in example 3, it says you purchasing a new car, the possible manufacturers, car sizes, and colors are listed in the table. So we have Ford, GM, and Honda. Car size, we have 2, and then colors, we have 4 colors. We want to know how many different ways you can select one manufacturer, one car size, and one color. We're going to skip the tree diagram to check, but I'll leave that to you guys. All right, so let's go ahead and look. So to choose the manufacturer, well, we have 3 possibilities. The car size, well, we have 2 possibilities. And the color, we have 4 possibilities. Okay, and it says that in order to find the total number of outcomes, we can simply take each of those choices and multiply them. So the total number of outcomes is equal to 3 times 2 times 4, which is simply 24. So we have 24 possible outcomes or possible vehicles that we could choose from. Okay, so that is the fundamental counting principle. All right, so what if we're talking about a combination? So it says the access code for the car's security system consists of 4 digits. Each digit can be any number from 0 through 9. How many codes are possible when, part A, it says each digit can be used only once and not repeated. Okay, so what I would do on this is I would start by saying, well, we have 4 codes. So I'm going to say some number times some number times some number times some number. Okay. Now, if we chose the first digit, notice from the number of numbers from 0 through 9. Well, there's 10. Okay. So we've chosen 1. So that leaves us with 9 for the second choice. We've chosen another one, which leaves us with 8 for the third choice. And then finally, we choose 1 more, so that leaves us 7 for the last choice. Okay, and when we multiply these out, we get 5,040 possibilities or possible outcomes. Okay, so we're going to do the same thing down here. So this time it says they can be repeated. So I'm going to set this up. I've got some number times some number, times some number, times some number. Okay, if they can be repeated, well, that means that I have 10 to choose from on the first one. I have 10 to choose from on the second one, 10 on the third, and 10 on the fourth. Okay, and we multiply this out and we get 10,000 possible outcomes. Okay. And then finally, let's say that we have each digit can be repeated, but the first cannot be 0 or 1. Well, again, we have 4 combinations, or 4 numbers in our combination. The first digit cannot be 0 or 1, so that takes 2 of our possibilities away, so that's 8. Okay. Then we have 10 to choose from on the second one, 10 to choose from on the third one, and 10 to choose from on the fourth one. All right, so we have a total of 8,000 possible. Okay. All right, so we have 3 different types of probability. Okay, we've talked just a little bit ago about classical. We've been dealing with empirical, and then finally subjective. So classical is kind of the classic, you roll a die and what's the probability of the outcome. Empirical is based on data, and subjective is based on opinion. Okay, so to set this up, we're going to start with classical or theoretical probability. It's used when each outcome in a sample is equally likely to occur. Okay, and we set it up like this. We have the number of outcomes in the event E divided by the total number of outcomes in the sample space. Okay, so looking at this example, you roll a 6-sided die. We want to find the probability of each event. Rolling a 3, well, there's only one 3 on a die. So we have hey guys, could you turn your phones down? So rolling a 3, there's only one possible outcome here. We have a 3, so that's 1 out of every 6 possible outcomes. Okay, so again, we're going to write this like this. We've got probability event A is equal to 1 out of 6. Okay, so the probability of rolling a 7, so probability of B, well, there's no 7s on a die, so that'd be 0 out of 6, which is 0. And I guess we do need to convert this, or we can convert this part A into decimal, so this would be about 0.167. Okay, and then rolling a number less than 5. So this would be the probability of event C is equal to, well, the numbers less than 5 are 4, 3, 2, and 1. And so we have four outcomes divided by 6, which gives you about 0.667. Okay, and so that's finding the probability of events. Okay, then we have empirical probability. So empirical probability is based on observations obtained from probability experiments. And we can find them similar to how we did earlier. So we're looking at the frequency divided by the number of the total number of people within our survey. Okay, so let's go ahead and take a look at this example. So we have a company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart shows the results. What is the probability that the next adult surveyed will read only print books during the last year? Okay, so setting this up, we've got the probability of only print books. Okay, so this is our event. Okay, is equal to, well, the frequency or the number of times that we had people read only print books, well, that would be over here, so 578. And then the total number of people that we've surveyed is 1,490. We're going to simply simplify this. Okay, so that would be about 0.388, okay, or 38.8%. Okay, so that's our probability. All right. Next, let's go ahead and take a look at this next one. So it says a company is conducting a phone survey of randomly selected individuals to determine the age of social network site users. So far, 975 social network site users have been surveyed. The frequency distribution below shows the results. What is the probability that the next user surveyed will be between 23 and 35 years old? Okay, so notice that 23 to 35 years old, well, that's 312. So the probability of 23 to 35 is equal to, that'd be 312, so the number of people within that age range, divided by the total number of people in our, or the total sample size. Okay, and again, we're going to go ahead and convert this, so we get, it's actually just straight up equal to 0.32, or 32%. Okay. Next, the law of large numbers. So all this is saying is that if we were to repeat an experiment, so rolling a die over and over and over and over again, the empirical probability, so the probability of us actually doing that experiment, eventually approaches the actual probability of an event. So if I were to roll a die hundreds of thousands of times, the event that I rolled a 1 should come out to be about 1/6. So it should come out to be that about that. Okay, and then the last definition that we need to talk about, and we won't cover this one very in depth, but the subjective probability is the result from intuition-educated guesses or estimates. Okay, so we're going to use all this information. So the definitions of classical, empirical, and subjective probability to explain which of these are objective, or which of these probabilities fit with which of these, each of these examples. Okay, so it says in part A, it says the probability that you will get an A on your next test is 0.9. Now, because we have nothing that we can test this on, and the fact that your next test is not necessarily, it's not necessarily predictable by using your previous tests, we're going to go ahead and say that this is a subjective, so it's an opinion. So you believe that based on what you've done before and what you studied, we can say that this is very likely, but it's not necessarily calculable. All right, so next we're going to say, well, the probability of, or we're going to look at the probability that the voter chosen at random will be younger than 35 is 0.3. Okay, so in this case, we have information on our population. Okay, and so we're dealing with a sample or a population. So in this case, this would be an example of empirical. Okay, so this is based on data that we should already have. Okay, and then finally, the probability of winning a 1,000-ticket raffle is one ticket is 1 in 1,000, and so this one would be your classical or theoretical. So you have a 1 in 1,000 chance that you'll actually receive the prize. All right, so the range of probabilities rule. Okay, so probabilities have to be between 0 and 1. Okay, so they have to be at least 0 and no more than 1. All right, so you'll never have like a probability of 1.3 or 5.6. Okay, so they will always be between these two numbers. Now, if I were to draw this range and kind of label a few parts, so let's go ahead and label this part 0. This one would be 0.5. This would be 1. We'll do 0.75 and 0.25. All right, so if I were to label these and kind of tell you what each of these would be, so if you got a 0%, so this would be impossible. Okay, 25% would be unlikely. 50% is just an even chance, so 50-50. 75% is likely, and then 100% or 1 is certain. Okay. One other thing that I want you guys to note, okay, and this is an important one, is that we've talked about unusual before, but an event is unusual. Okay, so in this case, our unusual is a little bit different if it's less than 5% or 0.05. Okay, so if we find an event that's less than that, it is deemed unusual. All right, so now let's go ahead and talk about a complement. So a complement of an event E is the set of all outcomes that are not included in the event. Okay, and we denote it with this E with a little tick next to it. So this is E prime. Okay, so if I were to draw a picture of this, so if let's say I have this sample set, okay, and I have this sample in here, and we're going to call this E. E prime is all of this information on the outside of E. So it's all of this stuff outside of E. So it's everything that's not included in E. Okay, so some important things to note with this is that if we were to add the event, the probability of the event plus its complement, you should always end up with 1. Okay, if we're looking for the probability of the event and all we have is the complement, we can simply subtract it from 1, which remember 1 is 100%. Okay, so we're taking 100% and subtracting the probability of the complement to get our probability of the event. And the same works with the reverse. So the probability of our complement is just 1 minus the probability of the event. Okay, so let's go ahead and use this in example number 9. It says, using the frequency distribution in example number 7, find the probability of randomly selecting a social networking site user who is not 23 to 35 years old. Well, first of all, let's go ahead and look at what the probability of 23 to 35 was, right? And we said that the probability of them being between 23 to 35 was 0.32. So we've actually already done this work here. Okay, so in order to find the complement of the event, hold on. So this was 0.32. Okay, so in order to find the complement, so probability of, we'll say not 23 to 35 is, well, the complement is always just 1 minus whatever the event is. So 1 minus 0.32, which we get 68% or 0.68. Okay, so that's the probability that site users will not be 23 to 35 years old. Okay, so again, we simply subtracted it from the whole. All right, last couple of examples. It says the probability experiment of tossing a coin and a spinner is shown below. The spinner is equally likely to land on each number. Again, we're going to skip the tree diagram. I'll leave that to you guys. Actually, let's go ahead. Yeah, we're going to have to use the tree diagram here. So use a tree diagram to find the probability of each event. So let's go ahead and build a tree diagram. Okay, so we're tossing a coin and spinning a spinner. So tossing a coin, well, we have 2 possibilities, heads and tails. Okay, spinning the spinner, we have 8 possibilities. So we have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, same with this one. We have 1, 2, 3, 4, 5, 6, 7, and 8. I'm getting a little sloppy with my tree diagrams, but let's see, I'll make it a little nicer. Okay, so we want to find the probability of event A, so probability of tossing a tails and spinning an odd. Okay, so tossing a tails, well, there's 8 possible outcomes over here. Okay, so we're going to include all of them. However, over here we have how many odds? We have 1, 2, 3, 4 odds. Okay, so we have a total of 4 odds on this side and 8 possible outcomes on the other. So we have a total possible of 12 outcomes. And how many possibilities? Well, we have, if we count the bottom row up, we have a total number of 16 outcomes. So we have 12 over 16, which is approximately which is approximately 75%. Now, I did this one wrong. Okay, so it says it's tossing a tails and spinning an odd number. Okay, so in this case, I did do this one wrong. We'll go ahead and go back and fix this one really quickly. So this time, I'm gonna doing it correctly. I would say, well, tossing a tails, well, that's over on this side, and then we have how many odd numbers? Well, we have 1, 2, 3, 4 odd numbers over here. Okay, so the real probability of this would be 4 over a total of 16. So in fact, it is actually 25% or 0.25. Okay, so I apologize for that one. Okay, so let's go ahead and take a look at event B. It says we're going to be tossing a head, so this one's an or. So tossing a heads or spinning a spinner and getting a number greater than 3. So tossing a heads, we have 8 possible outcomes. Okay, and then looking for numbers greater than 3. Okay, so we've covered all of the heads, so we don't need to worry about those anymore. But numbers greater than 3, well, that'd be this one, this one, this one, this one, and this one. So we have 5 over here. So the probability of tossing a heads or a number greater than 3 is equal to, well, 8 plus 5 is 13 over 16, which is approximately 0.813. Okay, so let's do one more example, and then we'll be done with this these notes. So it says your college ID number consists of 8 digits. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. Each digit 0 through 9. Each digit can be 0 through 9 and can be repeated. What is the probability of getting your college ID number when generating 8 digits? Okay, when randomly generating 8 digits. So the probability of the first one is 10. Then we have 10. We have 10 choices on each of these because they can be repeated. Okay, and when we multiply these out, we get a 1 with 8 zeros behind it. Okay, and that just happens to be 100 million. Okay, now we're looking at what the probability of getting your college ID number. Okay, so the probability of getting your ID is equal to, well, it's the number of outcomes that we want. We want exactly one college ID number, so we have 1 over the total number of possible outcomes, which is 100 million. Okay, and then we simply can divide those out, and we get 0.000. There should be 7 zeros before you get to the 1. Okay, so this is the probability that that you'll get your college ID number by randomly generating it once. Okay, that's also, let's see, that would be 0.234551%. So it's a really, really small chance that it'll happen.